here. Go up to screen mirroring. And, yeah. So let's see that. Yeah, I think it's mirroring. There we go. Nice. Sorry, it doesn't like me full screening it. Okay.
All right, there we go. All right, our next speaker is Manish Purohit, who will speak on new tools for peak memory scheduling.
Thanks, Kirk. Yeah, thanks for being here. I'm Manish from Google, and this is joint work with Surgeon, who was at MIT at the time and is now at Berkeley, and the rest of my group at Google, that's Zoya, Eric, and Joshua. Okay, so today I'm talking about new tools for peak memory scheduling. It's going to be a super informal talk, so not too much math, but it's focused on one problem. So please stop me whenever and ask me questions. It's a workshop on managing memory, so I don't need to tell you that it's important to manage memory. Here's a super out-of-date chart that shows, ML models are getting bigger and bigger, but hardware memory isn't increasing as fast. Sort of amazingly, transformers increased some 400 times in 2 years. Hardware memory may be like doubled. Okay, so the point of this is we need to manage memory better, especially when you're working with like a ML compiler. So I work in a group that helps with ML compilers, get an actual ML model, compile it to run well on TPUs or GPUs. Okay, so we need to schedule to minimize peak memory better. The talk will be in 2 parts. So part 1 are some general tools about how to think about peak memory scheduling, how to sort of approach it if you ever face it. And part 2 is applications to ML graphs in particular. Specifically, we'll be talking about series parallel graphs, and ignore the funny names on the ML part 2 for now. Okay, so beginning with part 1, some general tools. Here's roughly the problem that we face. We get some big graph. The graph looks like these graphs shown here. It's a DAG, so it's a directed graph, it's acyclic, and every node over here represents some computation. So think of a node as your favorite ML layer. So it's like a dot product, or it's a ReLU, or something like that, right? So every node is a computation. Each node, think of it as it produces one object. It produces one tensor, right? So it has some size. And you have an edge between nodes, and an edge represents sort of data dependency. So if an edge from node U to node V says like U produced some tensor that is used by V as an input. So what do we want to do given this graph? We look at this graph and we say, let's try to find a schedule for this. Like let's try to find an order in which we execute these computations. So we want a schedule to be a topological sort. So just a sort of a linear ordering of nodes. All edges go left to right. Great. And the memory model we care about is every node will produce some output, so produce one tensor of some input size. And this tensor or this output can only be released once it's fully used. Right? Once all of my consumers use my output, this memory can be released. Okay, so that's the model. And the goal is to find a schedule that will minimize the maximum memory consumption. Right? So at what point in the schedule do I need the most amount of memory? I want that to be as small as possible. And the motivation there is, a GPU has a finite memory size, memory limit. If your schedule needs more memory than that, it's just not going to fit, so you need to do more work.
So the graph is static?
The graph is static, yes.
And the nodes are labeled with the memory space. Is this true?
Yes, great question. So here's a quick run through of an example. So the problem looks like this. We're given a graph. It's some DAG. Here is just an entry. So we have 5 nodes, A, B, C, D, E. Every node has a size which says, okay, if you do node A, that will produce a tensor of size 100, let's say. Okay. So how does a schedule look like? A schedule for this simple example will look like, maybe you do A first. This produces a size 100 output. So your memory consumption is currently 100. Then you start doing B. So now you need to keep both A and the output of B in memory at the same time. So your memory is now 110. Once you're done with B, A has no more users, so you can release A, so A goes away. So now your memory is only 10 for now. Then you do C, so that's 60. Then you do D, so you need 50 more, so that's 110. Then you do E, but now you can let go of the C, right? So now you need 70 memory. Okay, so that's how the memory model is. Just to sort of hammer the point back in, if you do a different schedule, so let's say you do C and then D and then A, B, E, your memory consumption changes, right? And in particular, the second schedule in this case is much worse because you need a peak memory of 160. And so our goal is to find this schedule or this linear ordering so that the max memory consumption is minimized, is as low as possible. Okay, so that's the problem statement. If you've seen problems like this before, this should remind you of sort of well-studied TCS model, like pebbling games, right? So this is exactly a generalization of pebbling games, where each pebble has a size. And if you think of all these nodes have unit size, that's a pebbling game. So they want to find a strategy to keep pebbles on nodes of a graph, and you can only add a pebble on a node if all of its in-neighbors have pebbles. And the goal is to add a pebble on all the nodes eventually, and you minimize the max number of pebbles you used. Right? So that's a special case when everything is unit sized. Okay, so that's the problem statement. Yeah. I can stop for questions.
This looks a little similar to the synchronous data flow model, like by Edward Lee, embedded systems of, I think they studied.
Maybe, I don't know about that model.
I mean, it's slightly different in the sense that the nodes also have rates they produce, but they are also looking at the schedules where you keeping something in a buffer space and you have to hold that until the next node is ready. So I just
right, possible. But here everything is sort of instantaneous. So when you executing B, it produces the whole 10 at once.
But, excuse me, you have also not only memory requirement, but also processing time. So you don't
Right.
know, I mean, here it's not specified in the example when something is finished. So each job should have two numbers.
Good. So,
Am I right?
yes, that's right. But in the model, it's super simplified. So we don't care about sort of time at all. In some sense, it's an approximation. But in some sense, you can think of all schedules take the same amount of time, because it's just sum of processing times of each. That's not really true in practice, but let's pretend it is. So then all we care about is the memory. And there are other ways to model this problem. This one is what is called you produce before you consume. So in this case, for example, like node B here, will first allocate space for its output and then start using its input. So you need space for both. But there are other models considered. Okay, some things to keep in mind here are each node produces one output. Not one output per consumer. So it produces one output and gets released when all of its consumers have been scheduled. So it's like a node model instead of an edge model. Okay, sorry, going back. Good, so in theory I said, okay, this looks like pebbling games, it generalizes pebbling games. Go ahead.
So on your previous point, in particular, each node could have multiple arrows out
Yes.
of it, right?
Yeah, each node could have multiple arrows out of it, but this node gets sort of released once all of its users have been scheduled. Right, so going back to sort of the theory problem, this is pebbling games, or harder than that. We know it quite well. We know it's hard to approximate within any constant. It's not too hard to get like an optimal polylog competitive algorithm. So you can get approximate algorithm. So sort of standard techniques of balanced cut, partitioning will give you log n, square root log n, so log to the 3/2. Great, so in some sense it's closed in theory, but that's not super useful for like ML compilers for one, and as an applied theorist. So if you look at problems like these, you still get graphs like these in the compiler. So these are actually sort of my drawings of actual ML graphs that our compiler looks at, and you say, oh, we still want to find schedules for these. How do we do that, right? And these graphs are sort of super pretty, they're super simple and nice. They look sort of almost series parallel. Certainly they have low tree width and has a nice structure. So the first thing when we looked at these was like, can we sort of do something nice about these isolated graphs? So this subgraph looks sort of super isolated from the rest of the graph. So if I can just take this out, find a schedule for this, then plonk that back in, and solve the rest. Can we do that? Same thing for the question there. Okay, so that's how we started to look at these questions. Right, so our question we started off with, given a graph like this, if you take a subgraph which is sort of suitably isolated from the rest of the graph, can we replace it by its schedule? So can we sort of linearize a graph or not? Okay, so let's give, so this is an example. So a lot of the talk from now on is going to be a bunch of examples. Every example is trying to show sort of one step in our thinking process, right? So here's an example of an in-tree. So this is again an in-tree. So every node has only one user, moving to Aaron's point. And we want to do something like the following. I'm given an in-tree where I have some sync node T, and it has two children, U and V. Let's say it's a binary tree. I want to say, let's just solve the problem at U first. So find some schedule, it's a recursive strategy, to get a schedule for U. Let's get a schedule for V, and then we'll figure out how to combine the schedules to get one for T. Okay, so let's think about what's going to happen here to get some intuition for what's the problem you want to solve for U. Right? So if you look at the schedule for U, it's going to look like, it will give you some memory profile like the ones there. Here, sort of x-axis is sort of nodes or schedule, and the y-axis is the memory consumption. So if you do the schedule for U, it's going to give you some memory profile. It has some ups and downs. Let's say I call all the local maximas as peaks and all the local minimas as valleys. Right? So we look at the schedule for U, you get some memory profile with its own peaks and valleys. You get the same thing for V. And now if you look at these two schedules and try to get a schedule for the whole tree for T, it's going to look like, these memory profiles are going to stack on top of each other, right? So you're going to get something like this. So maybe you first compute the first 4 nodes of U's schedule, then you start doing some part of V, then you continue with the U schedule and so on, right? So that's the only way to, compute T from these schedules. You get some interleaving of those two schedules. Good, so now you get something like this. What do you care about? We care about minimizing the peak memory of the whole thing, or the whole graph. But now if you look at sort of these points in time, this is actually the peak of U plus the valley of V, right? So you had to go in the V thingy, wait at the V's valley, and then you go to the U's peak, right? So when you're trying to find good schedules for U and V, you don't really care only about minimizing their peaks. You somehow want the schedule for U to have good peaks and good valleys, right? So good peaks so that the peak is not too high, that's the objective, and good valleys so that when you are interleaving this with somebody else, you have a good stopping point, right? So you somehow want both of these at the same time. Okay.
So is the reason you don't just run U then V?
Yes, because maybe U, so this node, for example, is much lower than U, right? So maybe there's some good stopping point in the middle, right? So for example, let's say, right, so let's say you first do U first, then you have to pay for the space of U in the whole U in memory. But maybe this plus this is super large. So it's not enough to stop at U. Instead, what you could do maybe is, stop at this point and then do V. That will get you over the hump. Yeah, that's a great question. Okay, so this is where you're coming from. Good schedule needs good peaks, good valleys. Super vague, but that's what we, let's try to formalize that. Okay. Good, so I promised some general tools. So here's tool number 1. So tool number 1 is what we call as the node sum model. I'm going to give you yet another memory model. The point is, this is more general than the pebbling games one. It's simultaneously much simpler to think about. Right? So I don't want to think about these nodes and their out neighbors and whether it's still being used or not. So here's a much simpler but more general model. It's still a DAG, so the graph is still a directed acyclic graph. Every node has a weight, but now the weights can be positive or negative. Think of a positive weight node as someone that allocates new memory. A negative weight node is someone that frees up memory. You still want a topological sort of the nodes, but now the memory model is super simple. The memory model just says, if you have some schedule, the memory usage after the first I nodes is just the weight, the sum of weights of the first I nodes of that schedule. Right? So that's the memory model there. And the objective is to just minimize the maximum memory. Okay. So just to get the point home, here's an example. Not super important what the numbers are, but the point is if you do A, B, and C, you have to pay for all the 3 sizes together. That's 10 plus 5 plus 2, that's 17. Then if you schedule D, you can get the benefit of minus 10. So now you pay only 7 and so on. Okay, great. The picture sort of also shows why it's a generalization of the pebbling games. So think of this D as like a release node corresponding to A. So once A's users are done, you can schedule a release node to free up A's memory. Okay. Yeah.
Then 5 and 2.
Yeah.
But then 10 can be released, right? So 7, and then minus 10. So
That's right.
it should go down to minus 3.
No. Good. Yeah. Right. So here the memory model is different. The memory model is just the sum of weights of things that's scheduled. Right. So that's the sort of the benefit of it. Now you don't need to worry about, so node A has only a single effect. Whenever you schedule node A, you add 10 to memory. Whenever you schedule node D, you subtract 10 to memory. So just a much simpler model to think about.
Question? So, but does this come directly from the previous one, or is
It generalizes. So you can reduce any problem in the pebbling game model to this.
something like this?
Yes.
I'm guessing the reduction is not trivial because it seems like if I can't release G until I do I and H. So you need to keep track of these.
Yes. So in this case, so this comes from a reduction where there are no negative weight nodes. So if you sort of pretend the negative weight nodes didn't exist, that looks like a graph in the pebbling game, and this is the reduction of that one. Right, so this minus 5 corresponds to releasing C, actually. But that's not super important. But yeah, so this minus 5 corresponds to releasing C. Like C had one user, G. So you do C, then you do G, then you can release C. Right, like that's the reduction.
Nodes for release.
Yeah, so we sort of added new nodes for sort of releasing thing. But yeah, so that's just for intuition, but you don't really need to know. But yeah, that's just intuition. Okay, so that's the first tool. My talk promised tools, so we'll come to the next tool, which is dominance.
If you are using it as a reduction, that structure is a little specialized, right? Those release nodes
Yes.
have some
Yes.
nice properties.
Yes. Yes. It's certainly specialized, but we won't be using it.
Okay.
Also, the reduction is not as simple as what this shown. It needs somewhat technicalities. Okay, so schedule 2 is dominance. I said something vague earlier, like a good schedule has low peaks and low valleys. What does that mean? Let's try to formalize it. So suppose we have two schedules, sigma and pi. They both are schedules for the same graph. Then we say that sigma dominates pi if and only if the following 4 conditions are met, which is for any I, index I, any sort of position I in the schedule sigma, there is some index j or some position j in the schedule pi, such that if you look at the peak usage after I in sigma, that's lower than the peak usage after j in pi. Right? And the same is true for valleys. If you look at the minimum usage, like the best valley after I in sigma, that's still lower than the best valley after j in sigma. And the same is true for before. Right? So sort of 4 conditions, all symmetric. But the important thing is for any index I, there exists some j. Right? I think that's the right order of quantifiers. So here's a super simple example. Again, I have an out tree. Let's say we have 2 schedules here, A, B, C, D, E, F, and A, B, C, E, D, F. Right? So, and this is in the node sum model. Right? So if you look at these 2 schedules, sort of intuitively it's obvious that sigma is a better schedule than pi. Right? They both have the same peak memory. They both have a peak memory of 10. But somehow this pi does something stupid and uses like high memory over here again, whereas you don't need to. Right? And dominance sort of formalizes this notion. And it's sort of easy to see in this case that sigma does dominate pi. So if you look at any I for sigma, just think of it any node in sigma, you can look at the same node in pi, and that gives you the correct relationship. But the vice versa is not true. So pi does not dominate sigma. Okay, so that's the dominance relationship. It's a partial order over the space of all schedules. What's not clear is like does it have a maximum or not? So a dominant schedule is one that dominates everything else. Like it's like the best schedule for this subgraph. It's not all clear whether it exists or does not exist, but like that's the definition. Okay, great. So that's what dominance means. So the question was, we figure out, okay, so this sounds good. This looks like the right thing to do. You want low peaks, low valleys everywhere. But do they even exist? Like, do they exist for all graphs? Do they exist maybe for special node sum graphs that come from these pebbling reductions? Great. So we weren't sure how this goes. But the answer is yes. So like, one of our main results was, yes, all directed graphs do have a dominant schedule. And in fact, we can give a constructive algorithm for it, right? So yeah, so they always exist. Here's a constructive algorithm. It's constructive in the sense it doesn't take polynomial time. That's simply because like a dominant schedule is a peak memory minimum schedule, so that's of course NP hard, right? So you can't hope to get a polynomial time solution. But we say, oh, if you have an algorithm that gives you a peak memory schedule, you can convert that to a dominant schedule. Okay, so here's a super simple algorithm to get a dominant schedule for any subgraph. So let's say you're given a graph G, you first find a schedule that minimizes the peak memory. So this certainly exists, like that, like at most n factorial permutations. So look at those, find the one that has the lowest peak memory. Let h be the index of the first peak in sigma. So now you have these first h nodes, no? Sigma 1, sigma 2, sigma 3, and sigma h. Great. Let L be the topological cut of the graph of minimum total weight that still contains everything in the first h nodes, right? So it's a min weight topo cut that contains sigma 1 to sigma h, right? So intuitively it's like, is the first valley that contains this biggest peak. The best valley that contains this biggest peak. Now let lambda be the same schedule as sigma, but restricted to nodes in L, right? So restricted to nodes with the smallest value. That's it. So that's lambda. Take lambda out. So you take your graph L out and recurse on the remaining, right? So you return a concatenation. So return the first L nodes, L lambda, and then you recurse on the remaining. Okay. So that's go.
When you say topological cut, you mean prefix in that topological order, right?
Good. So topological cut just means it's a cut in the graph where all edges go from S to T. Like there's no edge going backwards.
Oh, so you're not starting with that schedule?
No.
Okay.
Yeah. Good. Yeah. So no, it's just some set of nodes in the graph that are all edges leave the cut, except this set must contain the first H nodes. Right. Yeah. So a lot of these are like not that can be in polynomial time, but we didn't care about it. Okay. So that's the model. That's the algorithm. I'm not going to prove it here, but the proof structure is roughly saying like, oh, this lambda subschedule that we found is good or without loss. Right. So what does that mean? It just means if you give me any other schedule pi, I can construct a new schedule pi prime that's better than yours. So pi prime will dominate pi, such that lambda is a prefix of pi prime. So I didn't make any mistakes by taking this lambda out, and then the proof will follow by induction because it's true on the remaining graph. Great. So that's the dominant schedule. That gives me to my third tool, final tool, which is going back to what I started off with. Isolated subgraphs and linearization. Not super important to see what isolated subgraphs are. This is actually a simplified definition. All it means is if you have a subgraph which you can remove the two endpoints and it disconnects the whole graph, that's isolated. So in this case, this ST, everything in the middle is isolated. What linearization shows is I can replace an entire subgraph by a dominant schedule for that subgraph. Right? So I'll take that subgraph out, solve the problem, like solve dominant schedules on that, and plunk it back in the whole graph, and I didn't lose anything. So there always exists a dominant schedule for the whole graph G that agrees with pi. Right? So then I can do this over and over again. Okay. Good. So that concludes my general tools. Now look at some specific applications to series parallel graphs. And one of my co-authors likes to title this part of the talk as trees, snakes, and lots of guesses. So this is going to be super informal. I'm going to bombard you with new graph families. So if you don't understand them, that's fine, but they're super simple. And this was a lot of fun. Okay, so first, what are series parallel graphs? This is standard. This is not new. Go ahead.
Can you solve the problem even if...
Good. So the question was, is dominance necessary property or not? It's required if you want to linearize things, right? So you cannot replace a subgraph with an arbitrary peak memory schedule and still hope to solve it.
But I think what you say is that if this property holds, then you can linearize
Yes.
the opposite, is it?
Not formally, but you certainly cannot linearize with an arbitrary peak memory schedule. So that's not true.
But it might be a weaker
It could be some weaker property. That's possible.
Okay, thank you.
Yeah, there could be some weaker property. Great. So trees, snakes, and lots of cases. Okay. So before we get to trees and snakes, let's look at what are series parallel graphs. So this is standard. Just to recap, a series parallel graph is defined recursively. So a single edge is series parallel with source node as the head, the sink node as the tail. That's series parallel. And you can have two operations. One is series composition, another is parallel composition. So what is series? If G1 and G2 are both series parallel graphs, you can combine the sink of G1 and the source of G2 to get a new series parallel graph. So that's over here. And what are parallel? If G1 and G2 are series parallel, you can combine the sources, combine the sinks, and you get a new series parallel graph. Right? So the family of series parallel graphs is like any graph that can be obtained this way. Okay, so that's series parallel. Actually, what we care about is like the directed version of this. So all edges are directed from the source to the sink, sort of in this case, sort of going down. Great. New graph families. This is what you call as a starborescence. So it's a star and an aborescence. So what do I mean by that? So the name is still TBD. Okay. So what do we care about here? It's an entry. So it's an entry. So it's a aborescence where all edges are directed towards the root. And so this one is an arbitrary entry over here. And we have a star on the top, right? So there's a star with a new node connected to all the leaves of the entry. Okay, so it's a star and an aborescence. Great, starborescence. Why do we care about this? We can first show, this is not super hard, that if you know how to solve a peak memory scheduling problem on a starborescence, you can solve it on general SP graphs, right? And this is simply because if you stare at a SP graph, you see that the innermost sort of parallel composition is always a starborescence, right? So then you take the starborescence out, you linearize it, so you replace it with the dominant schedule, and then you keep repeating. Right? So let's say we have the graph there. This diamond thingy is a starborescence. So I'll replace it with its dominant schedule. I'll get a new SP graph. I find the next starborescence. Let's say this is starborescence. I'll replace it with a linear schedule. Now this whole thing is a starborescence. So then I'll solve this. Okay. So starborescence to SP, sort of easy. That's how we want to do. Unfortunately, starborescence are not easy. So we don't know how to solve dominant schedules on the starborescences either. In fact, we show that it remains NP-hard. So it remains NP-hard even on sort of starborescence of this type, which is just a bunch of parallel paths. The problem is still NP-hard on a bunch of parallel paths. We call those pumpkins, by the way, in the paper. Okay, so let's look at a third graph family. Sure.
So you showed that like SP graph can be reduced to starborescence, but do we know that starborescences are strictly easier than SP graphs? Like, couldn't we just directly solve SP graphs? Maybe that's easier than starborescences.
Possible. Oh,
The starborescences are not SP graphs.
starborescence is RSP. Starborescence is RSP.
Because by doing extra whatever.
Yeah, starborescence is RSP. So yeah, so it's simpler. Great. So my last graph family is what we call caduceus graphs. Caduceus, if you don't know, or if you're not up to date on a Greek mythology, is a staff held by Hermes. So it looks like a staff with two snakes intertwined around it. So this is what we call as there are also wings, but we ignore the wings. Okay, so here's the caduceus graph, which is a staff, which is just a parallel path. Not parallel path, it's just a long path. That's a staff of the graph. And you can add as many snakes as you like. A snake is simply a path that has its start and end on the staff. Right? So in this case, this purple thing in the middle is a staff, and all the green ones are snakes. So a snake is just any path that both starts and ends on the staff. Okay, so that's a caduceus graph. Again, why am I talking about these? Because we show that if you can solve peak memory scheduling on a caduceus, you can solve it on a starborescence. Right? I won't go with reduction. It's not super hard. We can say, oh, if you start with a starborescence with out degree d, you can convert that to a node sum model. That's the node sum reduction. I won't really go into it. And if you stare at this node sum model a bit, it has only order d interesting nodes. So what really matters is the order in which you schedule these out neighbors of S and these nodes that are sort of higher in degree. So these yellow nodes. So there are only order d of those interesting nodes. Everything else is rather easy. Right? So then what you do is just guess the order in which these interesting nodes will appear. There are roughly d factorial guesses. So try every guess. For every guess, the remaining problem becomes the caduceus. Right? I won't go with that. But that's how the reduction will look like. So it's not polynomial time. It needs like d factorial guesses. But that's sort of required because the graph, the problem is NP complete for large D. So you need some exponential dependence in D anyway. Okay, great. So caduceus graphs. Can we find dominant schedule in caduceus graphs? Finally, the answer is yes. Not super easy, but you can do it. The paper has the algorithm and the proof. But okay, so finally we made a lot of different graph families. Finally, caduceus are easy enough that we can solve them. So here's the recap of the problem. You start an SP graph, you don't know what to do. You find the easiest star horizon inside it. That's like a tree with like a small cherry on top. You make many guesses. For each guess, you get a caduceus. You solve those, get the best of those. And that gives you a schedule for the whole thing. Okay, that's it. Thanks.
Questions?
So I guess there could sometimes be an advantage to forgetting information and recomputing it when you need it.
That's a great question. So yes, we can significantly improve the max.
Repeat the question.
Oh, repeat the question. The question was, is there an advantage to sometimes forgetting what we have already computed and maybe recomputing it later in the hope of reducing the total memory usage? And the answer is absolutely yes. So that's a whole different problem. We call it rematerialization. Because you can rematerialize your inputs to reduce memory. Much harder, and you can improve memory a lot more by that. What's harder is the resulting schedule can be exponentially long. So you can start off with like n nodes, but the optimal schedule can have like exponentially many n computations. But yes, that's it. Even for the unweighted case, it's piece-space hard to get the optimal rescale.
Does the nature of the problem become different if you have multiple nodes that you're allowed to do, rather than having a topological order? Let's say I tell you, oh, you have.
We didn't think about it.
Could you repeat the question?
Oh, sorry. So the question was, does the problem change a lot if you allow to do p nodes at the same time instead of a topological sort? And I don't have a good answer to that question because we never really thought much about it. My suspicion would be no, but we need to think about it.
You now have you have the parallel scheduling problem to solve.
Yeah, so you have a parallel scheduling problem, but we don't know how the memory adds up. So the memory consumption, like memory model, still needs to be formalized nicely, and I don't know a good way to do that yet.
In terms of relevance to the original motivation, is that equally relevant or equally irrelevant?
Oh, I think it's equally relevant. In the compilers, we currently do like a single pass, but you do it many times. So you do it once, and you say, oh, does this fit in the accelerator or not? If it doesn't fit, you split the problem up, and you schedule every part separately, and then keep repeating this.
All right, let's thank the speaker again. Just a note on schedule. So Martin is speaking this afternoon at 3:30. This is the CARP distinguisher, one of the CARP distinguished